So fantastic. Cheers for quietening down there without me even having to say anything. Right, so it's the last spoken session of the workshop, and we're going to have three speakers. One who's physically here, one who will be delivering a virtual presentation, but we do actually have physical backup on that. And then we'll be lastly going to Brian at the end, back to physical. So first up is Curtis McCulley talking about the LCO pipelines.
All right, so I'm going to tell you a little bit about what we do in terms of data reduction at Las Cumbres Observatory. We have a kind of an interesting problem. When Rachel originally asked me to give this talk, I wasn't precisely sure which direction I should go, but what I'm trying to do is I want to try to connect it to show you some of the technologies we use for the pipeline, which are often very similar to the type of things you can use for a TOM. Or these are things that you can hook into a TOM. So if you want to say, as you get an image coming in from a telescope, you might want to do some kind of data reduction on it. And so hopefully I can show you a few ways or a few pieces of technology that will help you do that. So I can't believe we've gotten through a workshop, and this is the first time this map has gotten shown. Usually this gets shown 27 times during our conference whenever there's a large contingent of Las Cumbres people here. So, in case you didn't know, Las Cumbres Observatory is operating 23 telescopes now. Is it 23 now? I lose count. 23? Yes, 23. So we have, instead of having one or two telescopes to deal with data reduction for, our data reduction problem is a little bit different. It's not the LSST type of data reduction where you have just enormous images. Instead, we are just massively parallel, and we have kind of regular size images, but we have 23 times them. And so, as you heard from John yesterday, you can have users submitting observations to any of these telescopes around the world. And LCO operates as a single system rather than a bunch of individual telescopes. You don't make requests, I want this 1 meter in Chile. That's not the type of system we do. Instead, we want to be able to just say, give me some 1 meter observation in the next 24 hours. And then the scheduler goes and figures out which it is. So kind of on the flip side of that, you want to be able to have a TOM say, where is my data? So that's kind of a theme of this whole talk is like, where is my data? What's happening to my data? And so one of the first pieces that we have is we have the user, the observation portal, which John showed yesterday. And one of the great things about this is it has a programmatic API that you can query automatically and figure out, is my request scheduled? Has it been finished? Is there data waiting for me? And these type of things as well. Once data gets taken, this is how we serve it to users. So we have an archive that we run out of the Amazon cloud. Now, this is mostly work done by Austin. So Austin did both the DOM Toolkit and before that, he had done a lot of the archive work. This is pretty much a giant S3 bucket for people who use AWS, and I'll tell you a little bit more about some of the statistics later on how much data we have in there. But this is a web front end. Oh, we're not sharing the video, I'm told. This very recursive thing going on. No, it's fine. So you have a way. To check what the status of your data is very easily and programmatically. You also have a way to get your data. So typically, the data is. Oh, wait. went the wrong direction. So, sorry. So you have we have this archive where users can download your data. As we move into time domain astronomy, one of the really important things is not only do we need to get observations on telescopes quickly, we need to get the data back to users quickly so that they can make decisions about how to deal with their upcoming observations. Is this really just a supernova? So we should cancel all the other observations if we're looking for a kilonova, things like that, things of that nature. Oh, this target's doing something interesting. We need to increase our observing cadence. And so that's kind of been the goal of this whole system that we put together. And so not only can you programmatically query the observation portal, you can also programmatically query the API and so, to the archive. And this allows you to both say, is data here? And it's allowing you to download it. And so this is something that you might be able to hit with your Tom, and you say, okay, check every 5 minutes, did I get new data? So this is something the Supernova Exchange does. And so you, if you want to look at any of the ways to do that, you can, the developers.lco.global link down there has all the information on how to do that. Now, one of the great things about this is this means that new data can show up in your Tom with zero human intervention. So we showed you the Supernova Exchange a little bit at the beginning of the week, and all of that data automatically populates. It pulls data from the archive automatically by checking this API, and then it does some extra reductions and sticks the results in the database. So our goal is to be fast. So how are we doing? Well, give or take, at the moment, we're able to, the median time from shutter close to data available to users in a reduced form is 10 minutes. So it's something we're continually working to improve, and I think we may be to about half that at this point. But one of the goals is we want to get people their data very, very quickly. So how do we do that? How do we manage to keep the data transfer rates down at some kind of reasonable amount? How do we deal with this large amount of data? So we process about 50,000 images a month. Again, we're not at the LSST data rates, but it's also non-trivial either. So we have several automatic systems set up. And basically, all of our pieces of infrastructure communicate to each other via queues. So we often use a technology called RabbitMQ, which I'll show you in a minute. But this has become one of the fundamental design principles that we've picked up over time and how to make the whole observatory operate together. So you have telescope, it produces an image and it writes the image to disk. So the shutter closes and it writes it to disk. And it puts it on a queue and says, hey, anybody who needs to get this data, it's ready for you to take off the hard drive. And then we have something at LCO, or well, at each site called the shipper, which then says, oh, I have a new file, I better ship that to LCO headquarters. It's then written to a hard disk at LCO. And then once it gets to LCO, it says, well, okay, we put it on a second queue. And anything else that needs to listen to that. So for example, we have a second one, which will then push it up into S3. But Bonzai, which is our pipeline, and on the first slide, the Bonzai Pipeline is what you see. That's what it's named after. But it tells the pipeline, oh, there's new data, it's time to go reduce data. And so everything is triggered automatically. So Bonzai is kind of just a listener. And it's just continually waiting, is there data for me to reduce? Is there data for me to reduce? This is very similar to, if you look at the Tom Toolkit, when you look at the asynchronous tasks tutorial, that talks about setting up either dramatic. Do we recommend dramatic or celery at this point? Dramatic right now, okay. So this is the same model for how we recommend that you do offline or asynchronous processing in a Tom. You have some kind of system with some worker that's listening to a set of tasks, or it's basically just a task worker that can go off and spin off kind of in parallel. So in the same way, once a file gets here, Bonzai can go do the processing in parallel without delaying the raw data getting to the archive. There's a lot of technologies. I really like RabbitMQ because for a couple of reasons, one of which is it gives you this queue technology, but it also gives you a really nice web interface along with it. And so it can tell you, oh, look, this is how many messages are on this queue and things like that. And so you can check, it's easier to check the status. So this is mostly just so you're aware of some of the technologies that exist. It's also got a built-in API. Again, everything, all of these different systems communicate via APIs. So what is our Bonzai pipeline? Well, really, it's an image reduction pipeline. And this projector doesn't do a great job of showing it, but it really is about removing the instrument signature. So you have raw data, and then we can combine it into a nice composite color image. Nothing too crazy, but we do produce astrometry. We do a basic source extraction, so we have some estimate of the image quality and a few things like that. Now, beyond that, we're really extending this to be a framework to write pipelines in general, trying to make it kind of a library that you can use. And so if you wanted to run a pipeline on your own Tom, we hope that at some point you'll be able to just import these stages, and it will make it very, very easy to implement those. It is on GitHub, so I think this is very important for data pipelines. So for observatory people in the room, like, pipelines should not be a black box. It shouldn't be an afterthought. Getting quality science requires that your input data is correct. If your raw data or your process data is wrong from the go, it doesn't matter how fancy your machine learning analysis is, you're still going to get the wrong answer. But if you're interested in anything that we're doing, please check us out. And like I said, as we're moving to trying to make this more of a library for pipelines in general, we hope that it will be useful for more people than just those at LCO. So I'm going to give you a preview of a few things we're going to talk about this afternoon in terms of deployment. There's kind of a big gap often between saying, oh, this pipeline runs on my local machine. And then you try to send that to somebody else and they say, oh, it doesn't work on my machine. Well, oh, do you have this installed? Oh, what version of this do you have? What version of Python do you have? Are you in a Conda environment? Are you in a lot of the same headaches that you guys have seen this week. So we need something that we're able to set up a pipeline or set up this version of the pipeline on any machine without having to worry about what the user really has installed. And one of the common tools to do that has become Docker. Docker allows you to build containers using these things. So this is basically just a recipe of everything you need to install the pipeline. It's actually kind of nice that I can fit all of that on one screen, because there are sometimes I've worked with pipelines over the years that said, oh, 10 pages of installation instructions. Anybody tried to install IRAF from source before? What this does is this creates something called a container. This is a binary image, and we've had several people ask about them this week if there's a Docker image for the Tom Toolkit, which is great, and I'm very happy about. But we're not quite there yet, but we will be soon. But in terms of the pipeline, I could give you this file, and you could have a version of Bonzai running very, very quickly. You could build this. And if I sent you the image, it's a 100 megabyte image or something like that, you could actually just start it up from Go. You don't have to install any other software besides Docker. So this has kind of become the same way. Containers are interesting beasts. They're kind of like virtual machines. They're not exactly, but that's kind of a good mental picture. And so the nice part is I can install this completely independently on my machine, and I can run it without affecting any of the other software on my machine. I don't have to worry about, oh, I have an IRAF installation here, or I have SciSoft installed over here, or I have Eureka installed over here. It's totally independent, and it's totally clean, but it doesn't have as much overhead as a true virtual machine. So it's kind of this nice halfway house. Now, for Bonzai in particular, because we are going to set up not just one container, there's actually multiple moving pieces to this. So, for example, say I wanted to set up a queue container, and I wanted to set up a Bonzai container to listen to that queue. So I can do things like I can group containers together. And to do that, we use a technology called Kubernetes, which is becoming very, very popular. And all Kubernetes does is it helps you spin up multiple containers. And it helps you manage those and basically deploys them all together. Now, this also gives us the benefit that we're now going to be able to run this very easily in AWS because our particular IT setup has a Kubernetes cluster set up in AWS. So we're going to go from operating at the LCO headquarters to operating in the cloud. And so we don't actually even need a physical machine to run the pipeline anymore. So speaking of moving to the archive, moving to AWS, just kind of give you an idea of some of the AWS technologies we're using. So our current archive lives in AWS in something called S3, which is secure, or what is it, simple, there you go, simple storage service, or S3. We have almost 10 million frames in our archive online stored in Amazon at the moment. And we have a little more than 80 terabytes in the system at the moment, and we're paying less than $1,500 a month. Really, when you think about the cost of an IT person to manage a machine, that's not bad. We have a very large machine at the building, and our IT guys tell us that the electricity to run that machine and the cooling to run that kind of machine is actually not too far off that $1,500 a month. It's so it's actually a very, very cost-efficient way for us to store data. Now, does it scale to LSST? That's a different question. But I think for places like the Liverpool telescope, I think it's a great piece of technology. It's also nice because then someone else has to worry about the uptime of your machines, and you don't have to worry about, oh, did I do this backup right? Or did this RAID card fail? Or some of the hardware issues that we often have to deal with. That's taken care of for us, basically. It also means that it's available all over the world. And Amazon has been laying a lot of extra fiber. And I'm not just, this is true of many of the companies. We're particularly using Amazon. This is true for Azure, that Microsoft runs. This is true for Google as well. Any of these cloud providers. But many of them are starting to lay cables, and Amazon specifically is starting to put points of presence all over the world. And so we are working on changing our data model, where we ship everything directly to Amazon rather than going through Santa Barbara first. It turns out that sometimes, it's not always true, but sometimes the hop to Santa Barbara is the slowest point in the chain, especially for places that don't have good connection to the rest of the worldwide internet. I think our lowest bandwidth site at this point is either Australia or South Africa. So you know how it goes. But Amazon now has a point of presence in South Africa, and so we can get onto their fibers much faster. And it means that we should have higher data integrity, and it should be faster to get data to our users. What's the other nice thing about having our data in Amazon is it's automatically available to everybody around the world. It's very easy to set up a front-end interface so that we don't have to worry about, people are downloading things from our actual physical machines in our building. It's something that's easier to access around the world. It also means that we can just put Amazon in the cloud. And then we can parallelize it because Bonzai is designed to scale horizontally. And if we wanted to, say, reduce all of the LCO data ever taken, you do that. We just have to spin up that many instances in Amazon. And so it scales a lot better. We're hoping that this change makes it more robust, and we're hoping that it makes it a little faster and easier to deal with. My last few minutes, I want to show you also something else you can think about in terms of Tom. So one of the problems we have is when you run an observatory, if any of you observatory people know that telescopes fail in really exciting and interesting ways. And if you have them integrated into a system, like a Tom system, or in our case, just integrated into the observatory system as closely as they can be very useful in detecting and sometimes storing these results. So we store a lot of our results in a NoSQL stack called Elasticsearch. That's probably overkill for what most people are going to do with Toms, but I could definitely imagine setting up some processing that does checking on an image as it comes in, and you say, okay, I have a new image on a supernova, and it passes this test, but fails this test, and storing that in your database. And so then you start to be able to connect the data analysis into your Tom and take advantage of it. So for example, this is a daily report we get that tells us about the image quality of all of our telescopes. It tells us how old our flat fields are, things like that. And so I imagine that there's a lot of use you could get from hooking a pipeline into the data hooks, which I think most people talked a little bit about code hooks yesterday, I hope. Is that true? Good. So this is some of the things you could do with a code hook, is you could run some piece of analysis software and store the results in a Tom database, similar to what we do. You can generate Slack alerts, things like that. Your Tom can have an issue, it detects an issue in an image, it can trigger a Slack alert and say, hey, something's broken. This one says, at least one of these events, the instrument probably needs to be restarted. And so 1 minute later, Elizabeth went and said, Telbot, please go restart our instrument machine so that we can start getting data again. We're also starting to think about putting a web interface on the front of the pipeline. So I think one of the things that has really become apparent to me as we've been developing the Tom Toolkit is the kind of the future of GUIs is now, but it's also in a web browser. And it's a very, very straightforward way for people to interact with data at kind of a large scale. And then it's also much easier to work with a web browser. You always have a web browser on your device. You may not have whatever piece of analysis software on your device already installed. And so I think this is a good computational model, why we're here at the Tom Toolkit. So anyway, that's basically what I want to tell you today. Again, pipelines are not an afterthought. So if you've got a new instrument, they are just as crucial as actually designing the instrument. There's a lot of technologies, and these are just a few of the technologies we've used for pipelines, but they're very similar tools that you can use for Tom Toolkit kind of things. If you have questions, let me know. And it is a good model to be able to integrate all these pieces of analysis together. And that makes it a very, very powerful tool. So you can both manage your data flow, but it also allows you to flag problems faster and hopefully do better science. So thanks.
Fantastic.
Yeah.
So that was really good.
Good.
Any questions for Curtis? Right. Let's in over here.
Do you use some cold storage facilities for your archive, or do you store everything in S3? Do you use Glacier or something like this to reduce cost of your archive? Because obviously you don't use all your 1 million feeds every day.
Right. Yes. So we have, it's on this slide. So what you can't read on this thing is this says standard, and that says IA for infrequent access. And so about 2/3 or 3/4 of the data is in infrequent access, and then everything else is in regular access. And so most of our data is actually just in the normal, about 1/4 of our data is in just the normal S3 storage. And it's not really that expensive. And then the rest, about 3/4 of it is to IA, to infrequent access, which is cheaper. That's right.
Does the pipeline does a spectroscopic reduction or just imaging?
That's a yeah, that's a great question. So we're actually working on a reasonably sized project to make it do the rest of the spectroscopic reduction as well. And so it's been great talking to people at the LT who are interested. I've been talking to people at SOAR and Gemini about how they're doing their spectroscopic reductions as well. Yeah, so that's something we're actively trying to do. My goal in the long run is to have Bonzai be just a framework on here, are basically the glue for the pieces of the pipeline, and then you can stick whatever you want in between to make it so that you can do any kind of reduction you want. Sure, yes. Yes, that's right.
Sorry, yeah, I was just mentioning that there does exist, I don't know if maybe would not be a pipeline by Curtis standards, but a collection of scripts that reduce spectroscopic data from the Floyd's instrument, and I guess there's something for the NRES as well that will give you an automatically reduced data product. You might have to go and tweak some things manually because it's more complicated than imaging, but you get more than just the raw data.
That's right, yeah. All the data we get, you get some kind of reduced data. Yeah. And so we're very active trying to do those spectroscopic reductions right now. That's right, yeah.
Just a comment and then a question. The comment, which may be divisive or whatever, is that I'm a great fan of Docker, by the way. So right,
Yep.
But Docker the company is in trouble. So who knows where that's going to go?
That's right.
Looking at your presentation, what I call the buzzword count is very high.
Yes.
You've got Docker, Kubernetes, RabbitMQ, NoSQL, Elasticsearch. Who's driving that? Is anybody actually sort of? I mean, how's the software stack being developed? Did you just get a new software engineer that says, well, I've got a new thing that I like, and you just stick it in there? Or is somebody actually trying to make sure that these things all work properly together?
It's a little bit of both. So we are trying to keep up on the software and what other companies are doing, and Austin can probably speak to this as much as I can. But we also have very good IT people who are saying, you should go down this road and you should not go down this road because they've done a huge amount of reading on which technologies are going. We went to OSCON, 2 years ago, and every other talk was talking about how Kubernetes has changed their life, for example. And so, we're not trying to we're trying to make sure we don't just end up on bandwagons, but we are trying to use the tools that industry is building for us. And Austin could say more about that. Yeah, sure. Right. Right. And, yes, Docker is in trouble, but the idea of containers is not going to go away. If it's not Docker, it's going to be something close to it.
Fantastic. Okay, if there's no more questions, we'll thank Curtis once again. Rachel's going to do some AV wizardry now, and we'll have Gregory Dubois Feldman coming in from France.
Dubois Felsman. No, I'm coming in from Pasadena. Actually, I'm afraid I'm laid up with a broken bone in my foot.
Injured and is unable to join us in person, and for that reason, he is hopefully about to give his talk.
Can you hear me? Hello? Hello? Hello, are you able to hear me? Hello?
Hi, Gregory, yep.
Good. You can hear me now. Yes?
Yep, that's fine.
Okay. All right. I will.
Gregory, you should be able to take control of the screen.
Okay, very good. Actually, I was planning to share from here, as you suggested.
Yes, that should be fine.
Okay, so I'm going to try sharing right now. It looks like I'm getting the reflection of it back.
That's right. We see it.
Okay, very good. Okay. All right, well, I'll go ahead here. So I am speaking on behalf of the LSST data management scientist, Leanne Guy, who's unfortunately double booked. There's an LSST workshop in Europe that is going on as well. I am the LSST Science Platform scientist, and Leanne and I have been working together for a couple of years on this already. And I'm going to tell you about the LSST Science Platform, which is the interface that we will provide for user access to and analysis of our data. So I'm sure most people in the audience are very familiar with LSST. I have just a reminder here for all of you. It's an 8.4 meter telescope with a very wide field of view, leading to an exceptionally high étendue for performing all-sky surveys. We have a 3.2 gigapixel camera and the ability to take images in 6 filters, the traditional UGR-ZY set. This is a fully automated survey and also a fully automated data processing system to go along with it. And it will produce up to about 20 terabytes of data every night, as well as up to about 10 million transient alerts. And the science platform is the interactive data analysis and data access and analysis environment that we will provide to go along with this. As a reminder, LSST was motivated by 4 what we call science drivers, 4 main science programs that were the justification for constructing this facility. Study of dark matter and dark energy, which for the most part involves large-scale statistical analyses of the entire sky covered by the survey to acquire high-precision data on various cosmological parameters. Cataloging the solar system by observing and measuring the motions of a large number of moving objects in the solar system, from near-Earth objects to main belt asteroids to outer solar system objects, and characterizing potentially hazardous asteroids for their significance for life on Earth, and cataloging the solar system at large as a way of understanding its history and its origins. Milky Way structure, in a way that's very complementary with Gaia, we will collect a comprehensive data set on objects in the Milky Way and its halos, and study its structure and evolutionary history by looking at the characteristics and motions of these objects. And then finally exploring the transient sky. Since LSST can observe the same place in the sky many, many times over its lifetime, we'll be able to produce an immense catalog of variability, both sort of familiar type objects, variable stars, explosive variables like supernovae, and explore parts of the variability phase space that have been difficult to cover before. The core of LSST is to perform a 10-year survey of half the sky. We call this the Wide, Fast, Deep survey because it meets all 3 of those goals at once. So what you can see on the left is a statistical summary of the number of times that LSST will visit each field on the sky in ecliptic coordinates here. Equatorial coordinates. You can see that the Wide, Fast, Deep survey region is the region shown in blue, where we're targeting 824 visits for each field across the 6 filters in 10 years. And there are extensions of the survey that we'll perform, as you can see, in the regions outlined in green, and I'll have a little bit more to say about that on the subsequent slide. On the right, you see the time structure of the survey. The upper part shows the time difference between visits to the same place in the sky in any filter. And the median of that distribution is 2 days. And then on the bottom, we show the equivalent time structure for revisits in a single filter, in particular in the R band. And you can see there the median is about 8 days for revisits in the same filter. The U-band filter is used only during dark times, so the revisit interval there is of course a lunation rather than the ones shown for the other filters here. So in addition to the wide, fast, deep survey, we will also do what we call special programs. They are accommodated in about 10% of the observing time that's not committed to the wide, fast, deep survey. We are still evaluating proposals for special programs. What we know for sure is that we will be doing deep drilling in a selection of fields. A few of them have already been announced. They're coordinated with well-known astronomical community fields that have been visited by many, many observatories in the southern sky. But you can see also our expectation that there will be special program surveys to cover the North Ecliptic Spur, the South Celestial Pole, and an extension of the galactic plane into the north. So the enormous amount of data that will be collected by the survey is handled by the LSST data management system. As I mentioned, we have about 20 terabytes of raw data per night. We take 30-second images, basically continuously. It takes about 5 seconds for the telescope to slew from one location to another. So the cadence varies from sort of 34 to about 40 seconds from visit to visit, depending on exactly how we operate the telescope and the camera. We're able to read out the camera in 2 seconds as part of that cadence. The processing of this data is carried out at 2 major levels. We perform processing on the night that generates transient alerts arising from comparing the images that are taken on that night with a template that's been built up over past observing. And we release alerts computed from those images within 60 seconds of their acquisition. And the rest of that processing on the night results in a catalog of transient and variable sources and calibrated images and difference images and solar system objects that are detected, and that is produced within 24 hours. The nightly alerts are released to community brokers worldwide that can then replicate those alerts and provide filtering services to the community. We've been participating in a series of community workshops about how that will work. And I'm sure many of you have seen presentations about that. LSST itself will also provide a basic alert filtering service that performs filtering just based on the properties of the LSST alerts themselves. Community brokers can extend that to include information from other sources. That processing is done nightly, as I said. Also, approximately once a year, we process the entire data set, so we do a cumulative reprocessing every year of the images and generate a catalog based on co-addition of the full depth, so that's increasing from year to year, of course, and then on analysis of the individual frames for instance, force photometry. And that produces a very extensive catalog of object properties, shape properties, photometric properties, astrometric properties, and time-dependent information from the single epoch photometry as well as force photometry. And those data products are released approximately once a year. The data products are released through the LSST project-provided data access centers in Chile and at NCSA in Illinois. And we also will accommodate the existence of independent data access centers that may be set up both in the US and in other countries. And the negotiations for the establishment of such services are still underway. Access to the LSST data, except for the alerts, is proprietary. The statement is that the US and Chilean astronomical communities have these data rights, and then data rights can be negotiated for in other countries through a process that's been established by the LSST project and the US funding agencies. So access to the data other than the alerts requires authentication to establish that the person doing so has these data rights. So the rest of this presentation is about the science platform, which is the means by which we will provide access through the data access centers to the prompt data products and the data release data products. To tell you just a little bit more about these, the prompt data products that are computed within 60 seconds include the stream of alerts, 10 million per night is our estimate. They're transmitted to alert distribution networks within 60 seconds of the camera readout. And then the catalogs that we derive from this analysis, as well as the calibrated images, are available within 24 hours. The intent of the prompt data products is to enable discovery and rapid follow-up of time domain events. The data release data products will produce catalogs of, we estimate, about 37 billion objects, of which about 20 billion are galaxies. This is detected on the COAD, so kind of a time-independent catalog. And then analysis of the individual images in the data releases will produce about 7 trillion sources, which will be associated with the objects, and about 30 trillion force source measurements. There are more force photometry measurements, of course, because we do measurements of faint sources detected on COADs on each individual image, even if the individual detections on those images are not statistically significant. We still produce force photometry no matter what. There will be 11 data releases, except for the first one. These will be produced annually. The first data release will be based on the first 6 months of data acquisition. We will also support user-generated data products. So we expect users to perform a wide variety of analyses, and they can either release to the community or share within collaborations value-added data products that they derive. So for instance, there might be analyses that are outside the scope of the project itself, such as shift and stack searches for faint Kuiper belt objects. The project is not expected to perform scientific classifications of objects. We characterize objects by the photometry that we see and other properties that we measure, but we don't attempt scientific classifications, such as a statement that this is a particular type of variable star or a particular class of supernovae. So users will be encouraged to perform such classifications and release those to the public, and we will support their releasing their own data products federated with the project-provided catalogs through the LSST science platform. About 10% of the LSST computing resources will be allocated for the generation and storage of these kinds of data products. So to get to the science platform itself, the vision for the science platform is a collaborative environment for doing LSST science to enable analysis of the data on the scale at which we will be providing it, to provide exploratory data analysis tools that let users browse through the data set using various metrics and visualize what they see, to enable high performance analyses by bringing the analysis close to the data and running it on our systems, support the user-generated data products that I mentioned, to integrate with other astronomical archives and tools via IVOA protocols, provide a collaborative working environment, and provide significant computing resources behind the system so that people can do large-scale analyses. The science platform is envisioned as having three what we call aspects that expose the data in different ways: a portal aspect, a notebook aspect, and an API aspect. The portal aspect is the thing that's most familiar probably to those who have seen the interfaces, particularly the web interfaces of existing astronomical archives, that will provide a query and visualization interface that is form-based and provides a visual user interface for performing data analysis. The notebook aspect, which I will describe in more detail later, is the environment for doing the next data analysis, where users do their own coding and analysis within the LSST hardware environment with high bandwidth access to the data. And then finally, the API aspect is simply refers to the fact that we expose the data to the community through programmatic protocols that are accessible over the internet that use community standard APIs, in particular IVOA APIs. The portal, the notebook, and the API aspects all rest on the same common infrastructure of the data release data, the alert filtering service, the user databases, user files, such as if like users perform their own custom coads, for instance, user computing resources, and a set of pre-installed software tools that users can extend with their own. So to say a bit more about each aspect now, the portal aspect is a visual window into the LSST archive and supports interactive exploratory analysis. So it provides visualization of LSST images, it provides selection and subsetting of data via form-based interfaces as well as via native ADQL queries, and provides a set of plotting tools with brushing and linking to let people connect analyses across many different plots of the same set of data. The notebook aspect allows users to perform more sophisticated next to the data analyses. It's based on the Jupyter Lab environment, which has now become very familiar in the community and is common to a lot of other cutting-edge astronomical archives. We provide a notebook-based, Python-based interface for access to the data with access to the same data interfaces, the same query interfaces that are used by the portal and that are available externally through the IVOA APIs, but now with high bandwidth internal connections. The users will have access to a pre-installed version of the full LSST software stack that was used to perform the data reductions, as well as a selection of community-generated tools, such as the tools from the PyViz environment. The visualization tools of the portal aspect are also available in this environment, so users will be able to transfer their knowledge from one aspect to another and work with familiar tools if they wish, or bring in other visualization tools from the Python ecosystem. As an example of what you can do in the notebook aspect, we here have a few images from a demonstration of using the Python community tools Bokeh, HoloViews, and Data Shader to analyze a set of data from DES, where on the left the data are plotted in sky coordinates, and on the right a color magnitude diagram has been set up. So this is something that you can do programmatically with Bokeh in the notebook aspect. You can also do it visually using the UI in the portal aspect. So these are, we're again emphasizing that the different aspects provide similar functionality and that people get to choose whether they want to work in a Python-driven way or in a UI-driven way. So in Bokeh, it's very easy now to perform a selection on a set of data. You can see someone has used the Bokeh lasso tool to select a set of points in the upper right-hand corner of the sky coordinate plot and then highlight the resulting data points in the color magnitude diagram. So one of the goals of having the science platform installed next to the data is to permit high throughput computation. We are looking at an environment where, despite the improvements over time in network performance, those don't grow as quickly as the improvements over time in compute and storage performance. And so we have a situation where the LSST data analysis challenge is kind of ahead of the availability of remote bandwidth for data analysis. And so we want to provide a bring your code to the data model for analyzing this data. We have a set of use cases that have been developed for these types of high throughput computations, generally ones that involve statistical analyses across most or all of the data set. So making stellar density maps, performing light curve fitting for interesting objects, performing feature computation on light curves to look for very specific details, generation of two-point correlation functions, and the training of machine learning models. So as a peek at the technologies that we are looking at for doing that, the use of these community tools I mentioned before, HoloViews and Data Shader, now extended with the high performance tabular data format called Parquet, and the use of the Dask tool for distributing an analysis over many workers. We were able to do density analyses on Gaia DR2 on the Gaia DR2 main catalog, which has 1.7 billion entries in it, in about 20 seconds for a recomputation to aggregate and rebin the data. And I don't know how well it's come through on the BlueJeans connections, but you can see already interesting and subtle structures in this density map that was computed in this way. Making it possible for an entire analysis like this to be done in 20 seconds enables a very wide variety of exploratory analyses of people trying out a lot of different things to see if they can tease out features from the data by changing their selection criteria or the functions that they use for aggregation and the like. Finally, I'll say something about the API aspect. This is primarily intended to allow integration with external tools. So we provide remote access to the data via web APIs. We have what we call a VO first strategy. We prefer to use IVOA protocols wherever possible. For instance, TAP for catalogs and SIA v2 for images. We have backend platform services that will be exposed through web APIs. So for instance, when you once you have identified an image in our catalog through SIA v2, you'll be able to get cutouts from that images via the SODA API. You'll be able to get the full image itself. And all of these protocols are ones that are supported by existing community tools to the largest extent possible. So for instance, we want to make sure that a tool like Topcat works successfully with the LSST data. So the user-facing aspects are built on top of a number of back-end services. We have database services. We have a distributed database product that we've developed in-house called QServe, which is able to handle efficiently queries over this tens of billions of row all-sky database that we'll be releasing. And the database supports queries via ADQL, which is mapped onto the native SQL dialect of QServe underneath. We also have file services for both project files and user files. And computing services, there are the computing services needed by the aspects themselves to perform their immediate user functions, to let the user log in through the network, to the notebook aspect and get a Python prompt or a terminal prompt, as well as additional computing resources that are available in a batch job-like way. To support collaborations, we allow the dynamic creation of user-defined groups. So users who already have data rights and are known to the system can set up new groups within that system at any time, reflecting a group of individuals within a single institution or across many institutions, and they will have access to this user-generated data product workspace and can keep files accessible only to the members of that group. So the workspaces are both file-based and database-based, so they can include both images and catalogs and persisted queries. And the user workspace is available from all three aspects. You'll be able to browse it from the portal. You'll be able to access it via IVOA and POSIX interfaces through the notebook aspect, and via VOSpace and WebDAV externally. This is all hosted at the LSST data facility at NCSA, as well as at additional data access center in Chile and other independent data access centers that, as I mentioned, may be set up in the future. The system was designed on a set of principles to be open source, to have a flexible deployment mechanism, and to use its own external interfaces internally. So the science platform is truly open source. We've used only open source community software underneath in its construction, and we release all our own LSST specific software as well. It's designed for ease of deployment. It's a fully containerized deployment based on Docker at the moment. We use Kubernetes for container orchestration. And LSST internally already deploys multiple instances of the science platform, from a single machine level for work that's being done right now on the summit with the instrumentation that's beginning to accumulate there, to several clusters at NCSA used for development and test and internal production purposes. And the VO first philosophy applies not only externally but also internally. We use these protocols inside, for instance, between the portal and the backend databases. So conceptually, the portal aspect and the notebook aspect both rest on the same web APIs and other middleware that we use. Those in turn provide access to the various components that I mentioned before, and then rest on the data access center infrastructure. And the intent is to have the user workflows able to use all three aspects as best suits the particular user's desires to work on-site, off-site, visually, programmatically, and they can move from one to another very flexibly as we go. We are engaged with the community to ensure that the science platform actually meets their needs. We have a process through the LSST science collaborations of getting input from people, but we've also taken some formal steps to get a review. So we had a review earlier this year that was staffed, where the review committee was staffed mainly by people from the science collaborations to evaluate both the vision and the design of the science platform and give us feedback on this. And the report is available publicly. The committee was very happy with our use of community and industry supported technologies to do much of the work, but yet to deliver an innovative experience out of assembling all of those pieces. There are some concerns that the community expressed about that we are still evolving certain aspects of the design, particularly the bulk data analysis using Dask that I spoke about earlier. That's still something where the technological landscape is changing so quickly that we're evaluating the tools as they go, and because we still have a few years to go to operations, are kind of still being flexible in that area. And not too surprisingly, the committee is worried that we may have underestimated how appealing this environment will be to the astronomical community and reminded us to take care that we be very readily scalable, which is something that we'd already planned on, so that if the demand does exceed the existing planned resources, that if the community and the funding agencies decide that it's a priority to scale up, that we can readily accommodate additional resources. So then I see I'm at the hour here. I do have a couple of slides on how the science platform will be made available to the community during the pre-operations period. Perhaps people can look at these online, or I don't know how flexible the timing is here. If I could spend another minute talking about this.
Yep, that'd be okay.
All right. So we have an activity called the Stack Club, which is a set of regular online meetings and a collaborative workspace that let people learn both about the LSST science pipelines code, which we call the LSST stack, and the science platform. This is open to members of the LSST science collaborations, and if you are a member of a science collaboration, you can, and you don't already know about this, you can contact your science collaboration chair to find out how to participate in the Stack Club. So we're already making prototypes of the science platform available right now through this process. And going on from that, we're going to be using the science platform in the commissioning era. We are starting this right now with the auxiliary telescope that's used for taking spectra to characterize the atmosphere. That telescope is coming online now. This activity will continue as we bring a commissioning camera online and then commission the full camera up through 2022 and our planned operations readiness review. So we will scale up the science platform through this period, and we will release 3 sets of data through the science platform for members of the community to look at. They're not going to be wide open. People will have to sign up for access, but this is intended to give you a preview of what the system will look like and us a preview of what your needs will really be, so that we can refine the system and make sure that it meets your needs in the operations era. And so this is my last slide that indicates when those will be available. I'm sorry for going over, and I thank you for your attention.
No, thank you, Gregory. If we can all thank Gregory. Okay, maybe time for a quick question. Okay.
So I think the, oh man, this is horrible. The science platform is really great. I mentioned this idea to Melissa a few weeks ago at Hotwired. I think it would be really cool if I could run a Jupyter notebook in the science platform, and then when I'm done with my analysis, I just click publish at the top, and then that makes it public, and then there's a DOI that I can cite in my paper that will take me to the Jupyter notebook and all the data there in one place. Obviously, you could do that now by just putting it in GitHub or something, but I'm thinking maybe LSST is a big enough force that it makes sense to have like a way to get DOIs directly in the science platform. Do you have any thoughts about that, or maybe you have a different model for what the best way is to do that?
So we have thought about that. There are a range of technical and kind of programmatic issues involved here. We would very much like to be able to make DOIs available for queries. We do have a requirement to have queries be able to be repeated, even if they're queries on a changing database, so that we have a mechanism to use timestamps to let people be able to repeat a query and get the same results that they got, even though the database has evolved since then, or of course to update it to the full current data. To go beyond that to DOIs that reference user-generated data sets raises issues of what the community expectations on the lifetime of DOIs are going to be. LSST's present arrangements with its funding agency don't let it make a commitment to be an archive beyond the lifetime of the survey. That may seem silly, but it's an important legality of our arrangements with the National Science Foundation. And so we're very aware of this issue and would like to find a solution to it. And the community clearly needs a way to generate really trustworthy, long-term, persistent references. The other problem is that the storage space that we have made available, based on that 10% rule that I mentioned, isn't really enough to encompass the kinds of things people will want to do with an LSST-style data set over the course of 10 years without taking some data down and bringing some back up. So we don't anticipate that users, once they've generated a data set, will always be able to keep it there forever. And again, that's that conflicts a bit with the expectations that people have of DOIs. I will say we're in communication with the agency about this, and the community is very interested in and sensitive to this. So we're going to try to find a solution. But right now, we don't have one. And I can only assure you that we share the vision of making a notebook publishable in a citable way is one that we share.
Thank you, Gregory. All right, if we can help. If we can thank Gregory once again. And now we've got Brian Miller for the last talk of the session.
Thanks. Okay, Gemini Part 2. In Episode 1 yesterday, we got to the point where you were able to submit your observations with the TOM. Gemini takes those observations, somehow gets them scheduled. We take the observations, you get data. Now we have to close the loop and get the data back to you so you can do the science, make any decisions about further follow-up or so on. So I'm going to be talking today mostly about the archive interface, because that may be the most useful thing for developing the TOMs, and a little bit about the data reduction. I'm speaking mainly on the behalf of the people who are doing this work. Paul Hurst and Ricardo Cardenas were the people that put together the archive system that I'll show you. And Joanna Thomas Ossip is the head of our user support department, which manages the data reduction and archive development. So yes, so we are basically gone through this. Yes. So when the data is taken at the telescope, of course, the files are written to the disk and eventually get to the archive, as I mentioned. In the morning, the cron job runs, which determines the programs for which the data has been taken, and will send an email out to the PIs whose email is in the OT, telling you the data is available, so that you know to go look in the archive. I think there's even a link to the archive here in that email. So then, in the morning, you would go to this system, which has been operational since about late 2015, after about 15 years where our archive was in the CADC. And that change was mainly done as a money-saving effort. And it's been developed and maintained by Gemini ever since. So here's the main URL there. The main interface looks like that. And you can get a little more information at this Gemini website here. So the system interface is fairly straightforward. You put in various search parameters like your program ID or the date or the type of instrument and the configuration, maybe searching for a target name. Click search and you get the results down here in this table. And you see lots of blue links here. You can click on any of those to get additional information about the data set. So for example, down here in this column, there's a P and a D. You click on the P, you get a preview image of that data set. If you click on the file name, you get the complete FITS header information. on this tab over here, you get all of the associated calibrations associated with the data that you searched for before, based on some built-in rules within the archive to find those calibrations. So it's pretty straightforward. It's a similar configuration for things that are dependent on the position of the telescope. It's things within some position within that some close to that position on the sky, and as close in time as possible. And this is what will be used by the pipeline later to do the automatic data reduction. The other tab in the interface is for the OBS logs. You can get the text version of the OBS logs so you can see some details of what happened that night. So this is how the data actually gets into the archive. Each summit has a version of this archive software which pulls the FITS files off of the file system as they're written. And then the information is passed on to the central archive, which is hosted at AWS. I think it's S3, just like the Les Cumbres system. And this is very fast. It typically takes about a minute to get a file from the file system into the archive. And of course, all of this is driven by APIs, of course, which are very useful for the TOM. So I'm going to spend most of the time going through the system. It's basically developing URLs based on this, add some feature that you want, and then some selection criteria, which it makes very easy then to send that to our system and get back your results. Here's, first, an example. The interface, you can see the URLs that the interface is using just by putting your cursor over some of these links. For example, there's putting something in this field here just changes the URL up there. Or you put your cursor over any one of these blue links you see down here, what the equivalent URL is. And so you can copy paste those URLs, into your notes, into your scripts, so you can repeat those searches or cause some action to happen. So this would be very easy to figure out what the URLs are, what the various features are available, and get that into your scripts or into your TOMs. Also, there are various actions here. If you mark these, file sets, then you can do bulk actions on this, like download the file, or this link here will download a tar file with everything that you selected. So I was going through and basically learning these various APIs. I found some things in our documentation that weren't quite complete or a little bit out of date, so I've tried to update that. So this file, this presentation may be a useful reference for that. And I also built a little library, Python library, which helped me in working with this and might help you in developing the TOMs. So that is now available on GitHub at this location here, or you can do a quick pip install. This might be useful for updating your TOMs later. So I'm going to go over a little bit about how that works. And these are the major features of the APIs which you may find useful. So one is this JSON summary, which provides a JSON equivalent output of the results from that basic search form on the web. So this may be one of the most popular things to use. One recommendation is you always add the /canonical option to the URL, so you get the very latest version of the file. It's possible to get previous versions for checking, what the history of the information, but the canonical gives the latest one. So if you use this library, you import this, set up your query string here, and then get the results just by calling this go@JSON subroutine, which handles all the JSON reference query and gives you back a JSON list. Then there's the JSON file list, which provides a little shorter version A little bit less information about the files that match your query. It's very similar. You set up your query in the same way, and now you put in the option of JSON file list, and you get back the resulting JSON list. I think as I review this is slightly wrong. I think you need to add an index in there to get that. You can look at the example script in GitHub to see something that has actually been tested and works. There's another interface to download files rather than the JSON information. So for example, if you want the preview of a file name, you can just give the file name to this GOA file subroutine. You can tell it where to download it, say option preview, and it'll download that JPEG image for it. Likewise, individual FITS file, the option file, it downloads the FITS file onto your disk. And finally, there's the option, just like with the UI, there was that button which you could download the tar file of everything. There's also an API equivalent. So you put in your query, you just go a file and say, give me the download option, and give you a tar file name, and it will download that, all the information into that tar file. And it's also possible to get all the information from the calibration associations. So unfortunately, when you query this, you get an XML representation of the data. So you can import your favorite XML parser, of course, then set up your query. And this uses a GOA Cal Manager routine. You get back this XML list, and you can parse that and find all the information. What it's doing, actually, it gives you a list of all the science files that match the query, and then under each of those is a big list of all the associated calibrations. So you can sort of go through this recursive method to find the information on all the calibration data, and then you can download the ones that you want from that. So all of that process will work for any data that's public in the archive. You don't need any authentication. But if you want to download proprietary data, which you will get if you get Gemini data as part of this process, you need to register with the archive. So you can request an account with this interface here, put in your username and your email, and you'll get access to the archive. The next step is to register the programs for which you have a program key, which provides you access to the data for that. This program key is sent to each PI when we create the program in the observing tool. You just enter your ID, your key, and then it'll appear in this list here, and then you'll be able to access that data. And then finally, in order to use the APIs with that, you have to obtain a web cookie, which you can get. There's information in the README in this GitHub account of how to get that cookie out of your browser. And you can store that in a file so that you can use it in your API with your scripts. One note is this cookie changes every time you log out of the system. So I recommend once you log in, don't log out again unless you need the cookie to change. You can log in multiple browsers as long as you don't log out from one of them. Then you just have to go through the process again and get a new cookie. So finally, the process to add the cookie to your requests. There's this little utility in this GOA library, which will read the cookie off of a hidden file on your disk, so you don't have to hard code your cookie into your scripts, and then just call the same thing, but with the cookie option there. And then you have access to your proprietary data. So that's most of the information about the archive and the API access to that. A little bit about data reduction. We have Gemini IRAF package right now, which is useful for getting science quality data reduction from all the Gemini instruments. Of course, IRAF is less and less support over time, and the Gemini IRAF package is dependent on, which means when the next version of Mac OS comes out, it will no longer run. So we've been in a long-term effort to convert everything from IRAF to pure Python. And that effort is starting to have results. A pure Python imaging package will be released later this year. And we've just started on spectroscopy reduction in Python as part of this GEMMA effort. As was mentioned, of course, now with EON and the GEMMA project, automated processing is now really a requirement. All our new instruments, such as Scorpio, are required to come with data reduction tools that work in our Python reduction environment, which is called Dragons. And you can get a little more information about that at this website here. The Gemini IRAF package now, which will still be required for doing spectroscopy, is easily to install with Anaconda. And the archive needs some development as part of all of this. Right now, it's really good for the raw data. It's rather limited in terms of handling reduced data, which it'll need to do. So we're in the process of hiring people to work on this, improve the user interface, improve the capabilities for reduced data products, the data provenance, like what version of the pipeline was used for reducing the data, provide better programmatic access to the data, perhaps some sort of streaming option so you don't have to be querying the archive all the time. And we need to change this authentication methods and avoid these cookies and use a system that will be compatible with the OCS upgrade system. So there's just one, hopefully just one authentication mechanism. And so finally, this is sort of an expanded list of what I gave yesterday of some ideas for improving the Gemini plugin toolkit. I think the main thing is maybe using this PyGOA library to add data download capabilities, such as what you can do with the Las Cumbres data now. As I mentioned, adding these options to run different guide star searches before your requests and displaying the images of the field. There are other things that have been mentioned, scraping our various instrument TO status pages, weather pages now. Unfortunately, there's no APIs for those yet, but scraping those pages would be useful. Adding a non-sidereal support if we change these URLs at the API for anyone who needs that. And, of course, processing the data, either by running this new Dragons pipeline when it comes out later in the year, or using the IRAF PyRAF package to do spectroscopy, which might need a little bit of interaction, although for basic long-sit reduction, that can be run non-interactively. And finally, how to get help. The main thing is our help desk system here. You can put in your question and it will get to the right person. There's a data reduction forum to handle your data reduction questions. And Gemini staff, it's a public forum, so other users may have answers to your question, or a Gemini staff person will try to address it. Or email me. I'm sort of this basic contact person for this effort, so any questions, send them to me, and I'll try to find the answer for you. So that's it for today. Thank you very much.
Yes, okay.
Just to start by relaying a question that's come in via the Slack channel. Gregory says, I have a question for Brian. Have you considered providing something like an astroquery.gemini in addition to PyGoa?
We could look into that. Yeah. This was just something I put together real quick, basically for this workshop, because I think it's something useful, but we could expand it to AstroQuery or something like that, yeah.
Yeah, AstroQuery has a pretty simple, common interface for doing...
I was just interested in the cookie, and that will be the way that people will integrate if they're going to be using the Tom Toolkit in the future. Does that cookie have an expiry date or a known expiry date?
I don't think so. I think it just changes if you log out of the system and log back in, it resets it.
Okay.
If it expires.
So the procedure would be that you log in with the web browser, just close that web browser down once you've got that cookie, and
right, log into the system.
Yeah.
The instructions for how to find the cookie depends on your browser, but those instructions, at least for the current versions of Safari, Firefox, and Chrome, are on the PyGOA GitHub page. stick that into a file, and that should be persistent until you log out of the
And you could close the web browser.
and then you can close the web browser. You can close the tab, bring it up again. As long as you don't click the log out button, it shouldn't change. At least that's my experience and understanding of how it works. I did it last night, and that's what happened. So.
Any other question?
So correct me if I'm wrong, but it seems to me like it's a really big problem that your spectroscopic reduction pipeline won't run on modern operating systems.
Yes.
So like what do you suggest I do if I have a Gemini Spectrum I need to reduce like today?
If you run a Mac, don't upgrade to Catalina.
Well,
otherwise,
too late for that.
Otherwise, I've been thinking about what to do because I'm basically staking on High Sierra for this reason. But I know I can't do that forever. I think what I'm going to end up doing is if I have to run the Gemini IRAF package, I will put it on a Linux virtual machine.
Yeah, I was going to say the other thing you can do is I built a Docker container to do just that because it does require 32 bits. And so that's another option if you're on Mac.
This is a strange question from David. It's a hangover from yesterday. He wants to know if a current observation gets into the archive quickly with TO comments on the weather, can he programmatically query the archive to get the current weather conditions?
Sure.
Works?
Yes, because there should be at least some basic information in the header, assuming the observer has been keeping up with, because it's a manual thing. The observer will set the current conditions, and that goes into the FITS header. So as long as that has been set properly, you get some idea of what the current conditions are. Yes. Yes. So that's another option besides scraping the weather page. Yes.
Okay, great. Any more questions? No? All right, well, we'll thank Brian and all of the speakers once again. Just Rachel now with some announcements.
Okay, so I am aware that a lot of you probably have flights to catch this later on in the afternoon. So before people start to disperse, I wanted just to spend a few minutes to acknowledge everybody that it took to put this workshop on. And this really starts with a shout out to our team, especially the software engineers who I know have put an enormous amount of effort into putting together not just the toolkit, but also all of the training materials for the hands-on session throughout the whole workshop itself. And also to Sandy Seal at the back there for all of her work that probably nobody noticed because it all went so smoothly. But you would certainly have noticed if anything had gone wrong. So thank you very much to all of the team here and also all of the people back at headquarters and around the world from LCO who helped to put all of this together. I'm really very privileged to work with such a terrific team. The whole program as a whole was not just a single LCO effort. I'd like to thank the foundations who have supported us from the very beginning, our partners at NOAO, Gemini, and SOAR in the observing proposal and the program that hopefully you guys are going to propose to, and also the LSST Corporation, who have also provided superb support materially and cheering us on from everything we've tried to do. And thank you to the SOC for all the work they put into preparing this science program and for the work that you're about to do in evaluating all of the proposals. I'd also like to thank our gracious hosts at Carnegie Observatories who really have gone to above and beyond to help us make this workshop run smoothly. And that's particular thanks to Beverly, Paul, Chris, and John for everything that they provided in support. And last but by no means least, thank you to all of you, for everyone who have proposed and everyone who have presented at this workshop. You have really made it a fantastic success, and it's been a pleasure working with you. And I will wrap up there, and you can all go for coffee. Thank you very much.